Welcome. In this video, we're going to continue on with the ways that we can count number of items. Now, one thing I wanted to add on to the previous video was taking a look at this example, number 4, in terms of how we can get 4-digit numbers. One thing you will have noticed in C was that each of those scenarios were actually a little bit different in their own right. Now, because we were looking for even numbers, we could have gotten even numbers in different ways. We could have gotten an even number by having a 0 at the end. We could have gotten an even number by having a 2 at the end. Or we could have gotten an even number by having a 4 at the end. Now, because each of those even numbers are unique in their own way, we can count the number of ways in which there is actually no overlap between these even numbers. Having a 0 at the end is completely different from having a 2 at the end, which is also completely different from having a 4 at the end. So because of that, what we call these are mutually exclusive events, which is basically another way of saying that you can add up the number of ways for each event because they do not have any overlap. They don't have anything in common with each other. So there's no overlap. And what I mean by no overlap is every item is kind of unique in their own way. You have the even number with 0 at the end, you have a unique even number with a 2 at the end, and you have a unique number with a 4 at the end. So those even numbers have no commonalities where they would overlap in terms of like a Venn diagram. Okay. Now, what we also did was, because we were able to add each of those mutually exclusive events, we give that a name too. What we used here is called the addition principle. So unlike the multiplication principle that you saw in the previous video, this is using what we call the addition principle, where you can add up the number of items in each event. Because they're all unique in their own way, they are mutually exclusive. Okay? So it uses mutually exclusive events. Okay, let's take a look at item number 5 now. How many 4-digit numbers contain no 8s or 9s? So as you take a look at 4-digit numbers, there's our 4 digits. We know that it cannot have any 8s or 9s. In the previous video, we also saw how you can't even have a 0 there in the first spot either, simply because if you have a 0 there, you really just have like a 3-digit number. That would not be a 4-digit number. So for that reason, we need to pick our numbers very carefully. You got to think about what each spot can actually hold. Now, because we can't have any 8s or 9s, we know that the choices we have in the first spot would be something like 1, 2, 3, 4, 5, 6, 7. Basically, you can pick 1 through 7. So you can't have any zeros there, otherwise you have a 3-digit number. So you can see here you have 7 choices in the first spot. In the next spot, now you actually can have zeros, right? That could be a 4-digit number with a 0 in the middle. And again, you can't have any 8s or 9s, so you've now extended the amount of items you can choose from 1 to 7 to 0 to 7. This problem makes no mention that you can't repeat numbers, so in this case you can. So we actually now have 8 choices to choose from. And again, in the next spot, you have 0 to 7 choices, and therefore, again, you have 8 choices to choose from. And on the last spot, again, you have 0 to 7, which means you have 8 choices to choose from. So multiplying those together, 7 times 8 times 8 times 8, gives you a value of 3,584 numbers. Okay, that's how many 4-digit numbers have no 8s or 9s. Numbers, let's just add there, do not have 8 or 9. Okay. All right, let's look at question number 6 now. How many 4-digit numbers contain at least 1, 8, or 9? Okay, so actually it sounds like this problem, number 6, actually vaguely resembles number 5. We're not looking for a 4-digit number that has at least an 8 or 9. I'm going to bring this back to how, earlier we were talking about Venn diagrams. I'm going to bring Venn diagrams back in this situation. I always find that visuals help in math. And so as I think about the Venn diagram for this particular case, what I'm seeing here is, with problem number 5, we were looking at numbers that didn't have 8 or 9s, and number 6 is looking for numbers that do have 8 or 9. So maybe what we're thinking of here is, here's all the numbers that could have 8. Here's all the numbers that could have 9. Of course, you have numbers that could have 8 and 9, right? That'd be the intersection of those two circles in the Venn diagram. But also, as we look at a universal set, we also see that all the numbers outside here contain no 8s or 9s. No 8 or 9. Oh, and that's actually problem number 5, isn't it? We know that in our Venn diagram, no 8s or 9s, there's 3,584 numbers. Now, if we think about the universal set, which is basically, everything you can think of, which is basically all 4-digit numbers, that's basically what the universal set is, then maybe we can actually find number 6 by saying, how can we find at least 1, 8, or 9? If I were to bring this into a simpler case, kind of bringing our Venn diagram to a more simple analogy, which is, let's say that we have an entire amount of, let's say, 10 things. And if we know that in particular, maybe something occupies 6 of those things, right? Then we know that if 6 things occupy this space, well, then that must mean that only 4 things occupy the rest of that space, because that's all that's left over. Okay? If we have a total of 10, then the 2 items must add up to be able to give you your actual total number. If 6 things actually exist within this spot, you got 6 items in that Venn diagram, then that must mean outside of that, you must have 4 items. That's what we call the complement principle, because they complement each other. In a way, you can think of this in geometry as well. If you have a right angle, you know that a 60-degree angle would have a complement of 30 degrees because they add up to give you 90 degrees. Similarly, if you have a total number of items, let's say n of a, it's equal to the universal set minus n a number of items that are not a. Okay, so, if we were looking at this in the Venn diagram, if we have a circle with a items, right? And the number of items that you see in here is basically taking your universal set and subtracting all the stuff that's not a. Taking this out, you'd actually only be left with the circle. You'd only have that. Okay? Similarly, we're going to use this formula and apply it to number 6. I'm sorry if that was a little bit of a long roundabout way to get to number 6 here. But the idea here is that if let's say we make the universal set equal, here's our universal set, which is the set of all 4-digit numbers, we can consider how we knew from problem number 5 that maybe A, that Venn diagram, that circle, would be all numbers that contain at least 1, 8, or 9. Okay, so if that's the case, here's our Venn diagram, and here's the universal set, and here's A, like all numbers that have 8 or 9 basically. Then what we can do is say, number of items in the universal set. How many items are there? How many 4-digit numbers are there? Well, if there's a 4-digit number, I know I can choose numbers 1 through 9 here. I can't have 0 here. I have 9 items to choose from. I can add in another 0 anywhere else. So basically I can choose 0 to 9, 0 to 9, 0 to 9. So I have 10 choices here, 10 choices here, 10 choices here. These are the number of items in the universal set, all 4-digit numbers. And if I take away all the numbers that contain no 8 or 9s, which is something that we know from problem number 5, if I subtract all the numbers that are not A, all the numbers that are have no 8 or 9s. In this case, we saw that was 7 times 8 times 8 times 8. Okay, we can subtract those. And what we'll end up getting is the number of items that actually do have 8 or 9. Everything left in the circle. Okay, and so if we just calculate that, this is exactly what we want to look for. So what we have is 9,000 minus 3,584. Okay, and then just putting that in, we see that we actually get 5,416 numbers that contain at least 1, 8, or 9. Okay, and that's using something called the complement principle.